you have the initial dynamics, which is dissipated, and so that's actually destroying quantum information about the initial state. But then after some time, you end up with like an encoded quantum state, and that further evolves under the unitary measurement dynamics. But because it's encoded now, it's actually protected from dissipation. So it undergoes unitary evolution. So the way this works is you connect to the previous plot. The dimension of the code space is just entropy density. So it's set by entropy density. Now as we're going through the space transition, at the critical point, this code space vanishes. And then the interesting aspect about this problem is that when it's in the success phase, it's not just encoding quantum information, it's actually doing it in an optimal way that achieves the capacity. So this type of dynamics of the system itself is sort of optimally protecting from future non-unitary evolution, which is an interesting aspect. And so we explored some applications of this in quantum error correction in this paper, which I won't say more about. And that's, from a more practical side, there's also been applications of this idea in topological quantum error correction. This paper from Hastings and Ha. These are called Cloquet codes, which use similar ideas. Okay, so now I want to change gears and talk about the implementation of this type of physics in an ion trap system. And so this is this paper I mentioned at the beginning. And so here, what we're going to do in this setting is we're actually going to move away from this one-dimensional model and take like a co-design approach to implementing this phase transition. So because of the generality of this phenomenon, we don't actually care too much about the details of the model, so that gives us a lot of flexibility in translating it to hardware. And so what we're going to the basic idea is to exploit the sort of strengths of the ion chain architecture. So one is they have this high fidelity 2-qubit gate, and they also have all-to-all connectivity. So that lets us sort of speed up the dynamics and get to the highly entangled states before noise affects the system. Okay, so the type of models we'll study are shown here. So we start in the encoded state. So this is some pre-encoding unitary. And then we'll do random XX gates, these Ising gates, at a specific angle, followed by measurements in a random basis. So we'll always do Z measurements, but we'll sort of randomly toggle between Hadamard and this effectively implements an X measurement because of the Hadamard. So we toggle between Z and X measurements. And I should say there's also a proposal from the IQC group, which thought about this for one-dimensional model. Okay, so this is the phase diagram for the model that we study. So we have the measurement rate, which is just the rate of measuring after these entangling gates. And we also have the measurement basis, which tells us whether we measure along X or Z. And for convenience, we're actually going to tune through the phase transition by fixing a measurement rate and just changing the basis. That lets us work at low measurement rates. So that was part of our co-design aspect, because this particular platform didn't have mid-circuit measurements at this point. So the measurements were expensive to implement, because you have to use Ancilla qubits. Okay, so this shows the actual types of circuits we ran, including all of the Ancilla used for measurements. There's also something we call a reference qubit, and the way this works is that we start the system entangled with one qubit, and this single qubit essentially tests whether there's a code space or quantum error code that survives the dynamics. And so if this reference qubit stays entangled or mixed at the end, then it's in the coding, then it's sort of in the coding phase, and if it purifies, then it's in the pure phase. So as I mentioned, we use Ancilla to purify the measurement. So this is a Z measurement, which is the Z0 gate, and then this is an X measurement. And then there's also this this sort of boxed circuit, this dash box circuit, which was really important for studying this experiment in like a scalable way. Because we're relying on random measurement outcomes, there's a post-selection issue that can arise in these types of experiments. So the way we get around it is we use like a decoder, which is similar to a quantum error correction decoder. And for these models, which are stabilizer circuits, we can actually analytically compute this quote decoder and act back on the reference system so that it always points in a particular state unless it's in a mixed state. And this type of problem I'm describing with a single reference cube, it also turns out to have some nice connections to problems in quantum gravity and the black hole information paradox. You can think of this as throwing a qubit into half an entangled qubit into the black hole and then trying to recover it from the Hawking radiation. Okay, so this is our experimental data showing the realization of these two phases I mentioned, this coding phase and or success phase and the failure phase. So here we're plotting the entropy of the reference qubit versus the number of gates applied in the system. And we're looking for the scaling limit where, as you scale up the system, the reference purifies more, and as in the failure phase, and as you scale up in the coding phase, it gets more entangled. And this is experimental data on up to 8 qubits with actually up to 4 measurements in the system, 12 qubits in total. And you can see these trends emerging clearly in the data in very good agreement with the theory. So this is really clear evidence of the two phases that we wanted to probe. Okay, so we're also very interested in probing the critical behavior of these models. And so we did work on looking at what type of requirements would be needed to actually see criticality in this system. In particular, we need longer time evolution. So that means you need to reduce heating that causes 2 qubit gates to become noisier. So mid-circuit measurements are becoming very important for reducing Ancilla overhead. And then we want to go to larger system sizes, but you can see from this plot, which shows a critical scaling, finite size scaling, that the system sizes we need are not out of reach in the near term. So we think that by the end of for example, the RQS, this will be experimental data. Okay, so I should point out that actually the IBM group, or not the IBM group, but academics working on the IBM machines were able to probe this phase transition in 1 dimension, but their approach was using just brute force tomography, so it likely wouldn't scale to systems larger than this large, for instance. So the nice aspect of our proposal is it's fully scalable. But these are still very beautiful, impressive experiments, of course, and demonstrate the basic physics. Okay, so this sort of ties into the final part of my talk, where I want to say a little bit about going beyond these stabilizer circuits, which are classically simulatable. But so we've been in the Scientrop experiment, we really heavily exploited these systems. So one is in quantum systems, it's quantum computers, it's very easy to implement stabilizer circuits. It's just tuning certain parameters of the gates. They also have this nice feature that because the entropy dynamics is it's very binary, it occurs in steps. So that makes it very robust to noise. You can filter out a lot of noise effects using that. And then there's this other feature that the decoders, you can actually compute them analytically using protocols which have been introduced. And so of course, the disadvantage is that it's a non-universal gate set. And so the physics can be quite different if you move beyond these stabilizer circuits. And even in the context of criticality, what we've been able to show through some very difficult numerical work led by Chet Pixley's group at Rutgers, we were able to demonstrate that this Clifford critical point and the R-random critical point are actually really distinct critical points with distinct critical properties. So it's important, even from physics viewpoint to actually distinguish these two gate sets in some sense. We know that from a computational perspective, the hard random gates we don't believe can be classically simulated, so that's already an important qualitative difference. But this is manifesting in some more conventional definitions of phases. Okay, so that's nice. So we now believe that these two critical points are actually different, and it would be nice to study it on quantum processors. But the difficulty when you move beyond Clifford circuits is you run into this decoding problem. We don't have efficient decoders for the system. And so that ties me into the last part of the talk, and I'll end on just a few slides discussing this sort of exploratory, more recent work with Mohammed Hafizi's group. And here the idea is to develop neural network decoders to attack this problem beyond stabilizing circuits. And so the basic idea, which I'll try to get across, is that we want to treat the decoding problem actually as an image classification problem, and then we can use these sort of well-developed tools for machine learning, that have been developed for image classification. And the reason that's a viable approach is that we're probing this phase by entangling with the reference qubit, and then the data that's coming out is actually just a measurement record of each space-time point. So it has this kind of two-dimensional structure. And what we want to see is that measurements which affect the reference qubit, they tend to occur inside a light cone. And so we can identify certain patterns which lead to essentially different states of the reference qubit by just studying different patterns within this light cone. And so that's very similar to image classification. So the precise task we're trying to achieve is, given a measurement record, we want to basically predict expectation values of this of the reference qubit along the different Pauli directions. And the learning task is you're given many samples from the quantum device, and you want to learn this function. That's what we're trying to do. And so here I motivated this by talking about going beyond stabilizer circuits. We have this funny issue that it's actually very difficult to generate data with non-Clifford circuits. So we first benchmarked this with stabilizer circuits because the method is actually very general. And so the nice aspect of this approach is that it only uses results of the quantum measurements as the input. And so it's actually potentially robust to coherent errors in the system. And as I mentioned, because of this difficulty to generate data on large systems, although we're actually working on that now, we're implementing this with our random circuits. We first studied it for stabilizer circuits where things are better understood. Okay, so this is the type of purification dynamics that occurs in these models. This is actually from the experiment. So you have some time evolution, and then in these Clifford circuits, the reference purifies at one particular space-time point. So we're essentially trying to learn where that occurred. And then this is showing some success of our learning algorithm, applied to really large-scale systems. This is like 200 qubits. And you can see that at least at short times, the learned dynamics follows the true dynamics, and that the scaling properties are favorable for this approach. So we think it's a viable approach to really study this on these near-term devices. Okay, and with that, I'll end with a summary. So these are the papers I'm highlighting, are the ones I focused on in the talk. So first, I talked about this link between these entanglement transitions and fault tolerance thresholds, which we were interested to explore. I talked about these I mentioned briefly these applications to quantum error correction. There's this idea of efficient probes, which is what we studied in the experiment. And then I mentioned this criticality between stabilizer circuits and numeric circuits. And finally, in this more exploratory direction, we were looking at applying machine learning tools to this decoding problem that arises in these measurement-induced phases. And this would be a strategy for really generic experiments. And again, I lost my last slide. So, which appears here. So, right, so some of the open questions in this topic. Right, so we really, one thing, and we're really moving in this direction, especially in the context of things like error mitigation, is to try and include more realistic features into these models so that we can really study this in a robust way. Another aspect is that we'd like to find ways to sort of characterize success phases that arise in these thresholds. I mean, one of the things you learn from this problem is that these models, there's a huge variety of different behaviors, and we'd like to move away from this simple dichotomy between success and failure. Another question which is of interest for quantum computing and maybe quantum simulation is whether instead of working deep in the below threshold phase, it can actually be practical to operate quantum computing systems near to these phase transitions using some of the different techniques that come up. So yeah, thanks to that. Thank you for your attention.
Last plot from the cationic experiment? There.
This is theory again. You want to
Could
go
you
to
go forward again to the slide just before your summary slide?
Oh yeah, that's yeah, good.
On the bottom left, how come there's a constant gap after T sub P, which is now blocked by the zoom link? After T sub P, there's this constant gap between simulation and experiment. What's the reason for that?
Yeah. Wait. Yeah, thanks for the question. Right. So yeah. So that's from noise in the system, and the way that so this is just gate noise. So like in the pure state is zero entropy, but there's always residual. There's a fair amount of noise that leads to residual entropy, and this is what we actually. So when I showed the data demonstrating the phases, we use this thresholding technique. So we take the data, we bin it according to where the entropy was for that particular circuit. If it's below a threshold, we call it pure, and if it's above, we call it mixed. And at the largest system sizes, these two distributions are starting to overlap quite a bit. So but yeah, that was another important way of getting over noise. And that's also specific to Clifford circuits again. So, thanks.
Yeah, you pick.
So about this last project with Mohammed, and people often complain that some of these sort of machine learning neural network things are kind of like black boxes, like give the answers, but you can't like understand what's going on inside. Is it kind of similar here, or can you actually maybe use it to learn something about your like error correction transitions and stuff?
Yeah, the way we had to do it was we had to sort of pick the black box that had the best chance to work. We tried a few black boxes. We had to sort of tailor it a bit more to our problem. So we do know a little bit of what's going on inside the machine.
And can you learn something from it? Like, can you like, oh, now I understand, like maybe some of your open questions, are they hiding in there?
Yeah, it's good. It's great. Yeah, it froze.
Zoom like really nice. Zoom thing really like coming back up. You're like already hit it once. Every time you escape.
Yeah, so I think I should say yes. So actually, this learning problem that we're describing, so we can formulate it very precisely the way we set it up as a type of Hamiltonian learn, like from the machine learning perspective, it's like a Hamiltonian learning problem. So you're given like a measurement record, and you want to predict like the probability of like a marginal distribution on the reference qubit. And so that there is actually like the full solution to the problem is like learning a Hamiltonian that describes the system. So Pradeep and I have been studying, without machine learning, just thinking about that question. And we actually find that, in Clifford circuits, there is a full efficient solution to the learning problem. If you use approaches like what we described here, that's not quite the best solution, but that lets you learn. What we've been able to show is you can learn the two phases, but the critical point becomes sort of unlearnable in the scaling of it. Of course. But actually, yeah, for Clifford circuits, we have other ways of doing this learning problem, and we do have solutions in that case. Yes. Thanks. Yeah, go ahead.
A follow-up Alex's question. Since your decoder is solving a similar, like, if you don't know now, like, decoder problem, but measurement, it has a time sequence. So it can be also construed as a language model problem, like a natural language processing. And I think a lot of benchmark different type of neural network decoder. Comparing CNN and language model of this can show that actually the language model is perform better. So I'm curious, like, what type of machine learning model you have considered and have already tried.
Yeah, I think we did. I think the same did try that just time-based approach. I think the spatial structure was important. That's why it didn't work as well. But this is the actual neural network we use. It has this convolution pooling, like 3 or 4 layers. Yeah. So this is an accurate.
Perform better than
Yeah, this performed better than convolutional. Yeah, you and
So one of the challenges of your traditional transportation problem is really making the number fit, how that across numerous classes. Find that as a challenge and how to do it.
Well, yeah, we studied big systems of hundreds of qubits. So the amount of data is impossible to learn or store. I mean, the general problem error correction. To sample all possible outcomes. Yeah, so I guess that's the sense that it's not overfitting because it's able to throw out all this useless data. But it's not a perfect. It does fail with some.
I think the phase transition of measurement is basically very fascinating. And one question is that phase transition point robust to any initial wave function? A lot of literature always think about starting from a quantum state, or the previous work from you is starting from a totally mixed state. You check if phase transition point is robust to any initial wave function?
Yeah, right. You might. Yeah, because it's a funny problem because we sort of measuring observables on the boundary, but from a many-body point of view, it's like a D+1 dimensional system. So the phase transition is in the bulk. I mean, there's some putative StatMech model describing this bulk of this problem, and so that's why we think physically at least the effects on the boundary don't change the bulk phase transition. One thing that can happen in higher dimensions is if you can actually have surface phase transitions. So depending on the initial state, you'll have critical points that are critical phenomena just on the surface of it. So if you ran this in 2+1 dimensions, it becomes a very rich problem. Since you can have.
Well, one question about that is if the mapping to E+1 condensed matter problem is possible, why is it not
Solved?
I mean, why is is it not foldable and also why is it not universal?
Well, I think, well, right now we know of two, at least for qubits, we know of two universality classes in the circuit setting. So one is Clifford circuits and the other is our random circuit, at least with all the phenomenology I described. There's actually other models which have yet other phase transitions. But right now we really just know of these two basic ones, the Clifford and the R random. But we believe the R random is really generic in the sense that if you took Hamiltonian evolution and interspersed it with measurements, you would get the same critical point. But yeah, and people have studied that and they see some evidence for that.
Yeah, one more second.
Follow up on this analogy. In a normal quantum phase transition, I can think of divergent length scales with the correlation. Are there any similar divergences here?
Yeah. Yeah, so like one thing where you can see the correlation, there's many ways to see the correlation length. But one way is you can look at the mutual information of two qubits which are far apart. And then the two phases, that'll essentially be zero. And then as you approach up to the exponential corrections, and then as you approach the critical point, you'll sort of develop this long range correlation between those two qubits. It still decays with distance because it's like a 2-point function, but it's parallel.
All right. If there are no more questions, let's thank Michael again.